It's a quite funny word. I don't know who invented this. Have you ever heard a mathematician use the word almost in a strict sense? That's a rare thing. Mathematicians usually like to be precise. But this is one word where in precise, rigorous mathematics, the word almost has a mathematical meaning. And the meaning is here. A function f is 0 almost everywhere if the set of values such that f is not 0. And then we look at this set, we look at the measure of this set is 0. Does this definition make sense to you? Almost. It almost does. Why? Because this notation almost everywhere depends on, again, with respect to what measure we are looking at. So actually we should make a bit of space here when we should say f is 0 mu almost everywhere. So from the point of view of the measure mu, f is 0 because outside the set of measure 0, f is not 0. Okay. Yes. What else is there to look? Can we calculate the measure of this set here? Yes, we can when f is a measurable function. So we might also say that a measurable function f is 0 mu almost everywhere if this is true. Why is this important? Because especially this fact. When is the integral of the absolute value of some function? What happens if this integral is 0? Or when is it 0 actually? It is 0 if and only if f is 0 mu almost everywhere. The proof. Why is this the case? Let's prove this direction. Let's assume that the integral is 0, and let's prove that then f must be 0 mu almost everywhere. How to prove this one? Well, now we will need to understand a bit of measure theory, but actually it follows quite nicely from monotonicity. So let's denote A as the set of those points for which f is not non-zero. We could also write it down as the set of points where the absolute value of f is strictly positive. We want to prove that this set A has measure 0. And to kind of get into grasps of this set, so let's approximate this set by some other sets, an, and let's say an is, we allow a threshold of 1 over n here. So what happens now is that an is a smaller set. We require a bit more. So an is contained in A, and actually, but when n grows, we are approaching A with these sets. Also, let's define a function h of n to be to be 1 over n indicator of this an. I leave it up to you to check that all these sets are measurable sets, all these functions are measurable functions. They need to be, and they are, but I trust that you are now able to do this verification. If I look at the value of this at some point s, this function hn, so what is the value of hn? So it is 1 over n if s is in an, it's 0 else, yeah. By definition, this function has only two possible values, this and that. And when hn takes this value, the point must be in the set an, and in that sense, in this set, 1 over n is less than the value of absolute value of s. So actually, we can conclude that this is always less than the absolute value of f. Also, we can conclude that hn is a non-negative function, right? So now we use the monotonicity of the integral. What does it imply? It implies that the integral of hn is less than the integral of the absolute value of f. What can we say about the integral here? By linearity, we can take this constant in front. So 1 over n comes to the constant. And then we have the integral of an indicator. And then we remember this is a special simple function that takes only that has only one possible value, non-zero value. And that's why for this indicator, the integral becomes the measure of this set an. Then what? Let's recall our assumption. We assume that this is true. We want to prove this claim here. What happens now from this condition is that this is 0. Yeah. On the other hand, on the left, we have this is at least 0. What's the only conclusion that we can make? The only conclusion that we can make is that the measure of an must be 0. I hope you agree with me on this. I hear no disagreement. So what next? What next is that now we can ask, what do we know about the measure of the full set, which is the measure of the union of these ans? We use the union bound. That's the union bound, which says that this is less than the sum from 1 to infinity mu an. But each one of these was 0, so there's nothing to sum. This is 0, and this was non-negative, so mu of a is 0. And that's actually what we wanted to prove. We wanted to prove that this set where f is not 0 has measure 0. So that's the one part of the proof. What about the other part? Let's leave that as a homework for you to think if you have time. So that's easier thing. This is the part of the proof that requires a bit of innovation. That think about these sets. The other direction is more like if you recall the definition of the integral and think about what kind of simple function could be there, so you get that proof quite nicely. This was the story about almost everywhere thing. So maybe we should highlight that if precisely 0 not needed here. What could be an example of a function that is not identically 0, but for which the integral would be 0? Could you think of some example? At this point of the course, you do have actually enough background, and I think we are all able to figure this out with a bit of thinking. So What would be this example? Let's do one example. Think about a concrete example where our space that we are studying. Let's take the real line now. Let's take the Borel sets now, and let's take the Lebesgue measure on the real line. Let's remember lambda is the Greek letter L, and that's L stand for Lebesgue here. So the Lebesgue measure on the real line, which is the only measure that assigns to every Borel set or every interval the length of the interval. And as a function, let's take a function which is 1 if x is a rational number and 0 else. Now you might actually recall the quiz that many of you have done before the lecture. So now we could also write this down, that this is the indicator of the rational numbers, this function. And then we could ask, okay, what's the integral of f with respect to the Lebesgue measure? Now the space where we integrate is the real line. Well, we are looking at the integral of a simple function. And this is a simple function. Q is a Borel set, so this is a pre-image of a Borel. This is a Borel set indicator, so it's a Borel measurable function. We know that for indicators, the integral is equal to the measure of that set that this is indicating. What's the Lebesgue measure of the rational numbers? That was part of the quiz, so it's a countable set. So we can also write it down as a union of all rationals, and then we take the singleton point. So that's why, let's fit it there. It's the measure of a countable union. We take the union of all points in the set, and then we take that singleton there. And that's why for countable sets, this is the sum of the measure of that singleton set. And what's the Lebesgue measure of a singleton set? Well, singleton set is an interval which has length 0, so every singleton set has Lebesgue measure 0, and we are summing 0, so there's nothing to sum, that's 0. The conclusion is that the indicator of the rational numbers integral Lebesgue measure is equal to 0, although of course this is a strongly non-zero function. On the other hand, we know that the indicator of Q is equal to 0 Lebesgue almost everywhere. So that's why here we have an example of an almost everywhere 0 function, because it's such a function, so it integrates to 0 as well. Time for questions.
Was it so that this is not Riemann integrable?
Very good question. That is actually leading us to the next topic. Which I planned for the table is actually Riemann integration.